Today, we're going to continue talking about zeros and poles of functions. So the first thing I'm going to remind you guys of is like what we did last time. I don't know if you noticed, for those of you that want to be able to trace through kind of what we did last time, I posted a video last night where I went back through the lecture. I didn't have my computer, so I didn't record the lecture, so I recorded sort of what I did in the lecture and posted it on the YouTube channel for the class. I'm recording this, but I'm also going to probably regularly start making these little 30-minute videos that go back through the lectures afterwards. If anybody's interested in the notes that I generate in the course of doing that, you can just ask and I'll give them to you. So last time, so we talked about poles of functions. And so let's go back through some of the basic ideas. So a function is meromorphic if f of z is equal to a of z over b of z, where a and b are analytic functions. And b is not identically 0. We'll talk about isolated singularities. So f has an isolated singularity if f is analytic on the deleted neighborhood of, so an isolated singularity at z is equal to z naught, if f is analytic on a deleted neighborhood of z naught. And then we said that isolated singularities come in 3 flavors, right? We said that we had removable singularities, and those are characterized by the limit as z goes to z naught of z minus z naught f of z 0. And then we had pole of order k, means that the limit as z goes to z naught of z minus z naught to the k plus 1 f of z was equal to 0. But we'll say k plus 1 is the smallest such number. Then we say f has a pole of order k at z naught. Z is equal to z naught. And the last possibility was an essential singularity. And those just happens when it's an isolated singularity that's not case 1 or case 2. Isolated, but not case 1 or case 2. So you're isolated, but you're neither. Yep?
Are all holomorphic functions meromorphic?
Yes, because they're all, holomorphic functions are a subclass of meromorphic functions. And likewise, when we actually build out formally Laurent series, Taylor series are all Laurent series. So the analytic functions are a subclass of the meromorphic functions. So if you want, you can think of these contain the analytic functions. Which really means the study of meromorphic functions includes the study of analytic functions in a useful way. The same way that all polynomials are rational. Yep.
So if we have multiple poles of various orders, will, after you get a pole at k, it goes to 0, but then if you go up another, does it return to a non-zero value?
What do you mean?
So, sorry, we have the limit as at k plus 1 of f of z is 0.
Yep.
If we increase k by 1,
that will still be 0. If this is 0, then hitting with another thing that goes to 0 will remain 0. The idea is that it's, you have a pole if there's some power of z to the k that you can multiply against f and take the limit and you get 0 out. And then the order is just the smallest power of z that you can use to do that. Okay. So you can imagine, we're actually going to talk, order is one of the first things we're going to talk about today. right? But basically, you can imagine here the idea is if you took the example, say, of f of z, here's a really dumb example, 1 over z to the third times z plus 1. If you took f and you multiplied it by, say, you took z to the k, f of z, and you took the limit as z goes to 0, if k is bigger than 3, that limit is 0, right? If you hit it with z to the 4th, z to the 5th, whatever, because what's happening is the z to the 5th is canceling the z to the 3rd, right? So if you say you picked k is equal to 5, you get a limit as z goes to 0 of z to the 5th f of z, which is z squared over z plus 1, which is 0, right?
So
And the order is just the smallest power of k that you can use that makes this true.
So this will only give you the order of the pole at z naught. It
Yes.
doesn't tell you-
Yeah, so these limits are calculated at each isolated singularity. So there's a different order for each one. So in this case, the order, I'm going to talk about orders of zeros today, which will, I think, like, we're going to connect this together. The order of the pole at z is equal to 0 is 3, because there's 3 copies of this z running around in the denominator. And likewise, the order of the pole at z is equal to -1 is 1, because there's just a single power of z down there. So if I multiplied by z squared, z plus 1 squared, and took the limit as z goes to -1, I get 0. But if I drop the value of k down even by 1, I don't get 0 anymore. Okay, so let's talk about order of zeros and poles. Okay, so the order of a zero of a function. I suppose it would be remiss of me not to define what a zero is of a function. So f of z has a 0 at z is equal to z naught if f of z naught is equal to 0. Okay. So we're going to do here, so what I want you to think about in the background here is that we're talking about analytic functions as the basis here, right? Meromorphic are built out of like polynomial or quotients of polynomials or quotients of analytic functions. And so I want to be operating with the assumption here that all the functions we're dealing with have convergent power series. Okay? So f has a 0 at z naught if f of z is z naught is equal to 0. What that will mean if you have a function that has a power series is you can say f has a 0 of order k at z minus z naught, sorry, at z is equal to z naught, if f of z is equal to z minus z naught to the k g of z. So I can factor out, just like in, when you learn this stuff for the first time and you're factoring polynomials, if I can factor out k copies of z minus z naught, and whatever is left behind is not equal to 0 at z naught. So f of z has k copies of z minus z naught that can be factored out, where g of z is analytic at z naught. So I can't just induce a singularity by dividing out so many z minus z naughts that I put a singularity in the denominator. And g of z naught is not equal to 0. So I can yank out all of the z, it's just you're factoring out copies of z minus z naught. So, for example, let's look at f of z is equal to z squared times the sine of z cubed. So this function has a lot of zeros in it. But let's in particular look at the 0 that exists at z is equal to 0. So claim is that z is equal to 0 is a 0 of f, because f of 0 is equal to 0 squared times the sine of 0 cubed, which is 0. So it is a 0 for the function. And so presumably, I can factor out a whole bunch of z's from this thing, and that will tell me what the order of the 0 is. Now, it's not immediately obvious. It's at least order 2, because there's 2 copies of z hanging out here. But I can't actually tell what the rest of the function is doing unless I do a power series expansion for it. We're going to be doing a lot of power series expansion over the next couple of weeks. So all the sort of geometric series and sines and cosines composition methods are all at play. So if I have, maybe I'll use a different color, and maybe it will work. Sine, so depressing. That's somebody else's problem solution here. All right, sine, put that in parentheses. Sine of z cubed is going to be equal to the sum from n equals 0 to infinity of minus 1 to the n z cubed to the 2n plus 1 over 2n plus 1 factorial. So you compose in the z cubed, and if you write down what that looks like as in the sort of expansion so you can see what's going on, what you're going to get is z cubed minus z to the ninth over 3 factorial plus z to the, okay, so the next 5 times 3 is 15, 5 factorial, and so on. But each one of those has a z cubed inside of it. So this is equal to z cubed times 1 minus z to the 6th over 3 factorial plus z to the 15th, z to the 12th over 5 factorial, and so on. And so the order of the 0 now should be apparent for the original function. Z squared sine z to the 3rd is the same as z squared times z to the 3rd times 1 minus z to the 6th, 3 factorial plus z to the 12th over 5 factorial, and so on. And that means there's this z to the 5th hanging out front. So this function, that's g of z. So we factored out all the copies of, that's the g of z that I wrote right here. I know that I'm finished if this function is analytic. Is it analytic? Well, it's got a power series with no negative terms, so it's an analytic function. Is it equal to 0 if I put in z is equal to 0? No, it evaluates to 1 if I put in z is equal to 0. So that means I've completely taken out all the relevant copies of z here. This function, g, has the property that g of 0 is equal to 1 and g of z is analytic at 0. I'm allowed to plug 0 into it, and it evaluates to not 0. So I'm finished with my factoring, and so the order of the 0 at 0 here is 5. The fact that I could pull this 5 copies of z out means that I've got a 5th order 0 at 0. Sorry about saying 0 so many times. So z is equal to 0 is a 0 of order 5 for f of z is equal to z squared sine z to the 3rd. So how do we use this idea when we're analyzing the order of poles? Well, what if I had g of z is equal to 1 over z squared times the sine of z to the 3rd? That function certainly has an isolated singularity at z is equal to 0. This has an isolated singularity at z is equal to 0. What is the order of, it's a pole, so my claim is that z is equal to 0 is a pole for this function. Z is equal to 0 is a pole of g of z. What order is it? It's 5, right? So the way that you another way of calculating the order of a pole is to calculate the order of the 0 of the function that you wrote, if you can write it this way. So for a meromorphic function, for a meromorphic function, the order of a pole of A of z over B of z is equal to the order of the corresponding 0 of the function B of z. So if I could calculate that this function has a 0 of order 5 at 0, then this thing has a pole of order 5 at 0. Yep?
Even if you have more zeros on A of z?
Well, there's more, I mean, so like, it could be the case, that, but when you do this calculation, implicit is the assumption that you've canceled out any common factors, right? So you want to do the reduced version of this. So prior to doing this computation, if you're doing it for real, is all of this presumes that you factor out common zeros. So I said that last time as a hypothesis, but you don't need it. It's just part of the process of computing the order is you just cancel out anything they've got in common. Okay? Yep?
That includes when they're like very not obvious.
It does include when they're not obvious. It's hard, right? Because you have to be able to, I mean, so the analysis is really easy when you're dealing with rational functions and things where it's very easy to produce the power series. And it's a lot more delicate when you just have a function and you know it's equal to 0, and you don't actually know the order to which that 0 exists. There's a more delicate analysis involved. And that's actually why frequently we use that limit calculation instead, because I can do that numerically. I can just increase the power of z minus z naught until I see the limit being equal to 0, and that's another way of detecting a limit of order k. Right? So if I don't have an obvious way of writing a power series down and factoring out some copy of z minus z naught, then I have to do something else, and the something else is using the limit argument instead. Okay. So it turns out to be the case that the order of poles and zeros is going to be a really important part of doing our approximation theory when we talk about meromorphic functions later. But the nice thing is, for rational functions, you can just read these things off. What this definition means is that for rational functions, you just immediately identify the order of everything. So I think, what was this example? It was like 1 over z cubed times z plus 1. That just means find the power of the term and say, oh, that's the order of the 0. So the power of the term in the denominator after you do any mutual cancellation is just equal to the order of the 0, or the order of the pole. Okay, so now we're going to talk about how we compute series around isolated singularities. And we're going to get a lot of ground out of this formula. 1 over 1 minus z is the sum of z to the n. All right. So, calculate a series expansion analytic on a deleted neighborhood of each isolated singularity of, what's a nice one to start with? How about 1 over z squared plus, no, not plus yet, minus 4. So the first thing you got to figure out is what are the isolated singularities of this thing? So f of z is 1 over z squared minus 4, which is 1 over z plus 2 and z minus 2. So what are the isolated singularities? Yeah, so z is equal to, z naught is equal to 2, and z naught is equal to minus 2. How am I going to do this? I want to write a series expansion. for this function, and I want to expand that series around this, say this value, and then I want to do a different expansion. I'm not going to be able to do it at the same time around the other value.
Can you do partial fraction decomposition and then enable the parts to look like that formula?
You can, although that is like, it's not usually the way that you do it. Okay, so you can do partial fractions, expand each function separately, and then add it back together again, but there's a faster way to do it. Yep?
Do some funky multiplication.
Funky multiplication, that's right. Okay, so I'll write that on the board, right? So we're going to do funky multiplication. So what is the goal if I'm trying to write a series that is centered at z0 is equal to 2? What will the terms of the power series look like? What is the variable term going to look like? So I'm going to have some series, and there's going to be some coefficients. What should go right here, raised to the n power, if I have a center at z0 is equal to 2? What should those be? Z minus 2, right? So I need a series that's expanded at z minus 2 if I'm centering it on this punctured disk. So essentially what we're saying is knock out the point at z is equal to 2 and then come up with a series that's analytic everywhere else inside. Well, I have a piece that already has a z minus 2 inside of it. It's this 1 over z minus 2. So if I could expand 1 over z plus 2 as a power series with these type of terms, I could just multiply that in at the end. So now, what I want to take here, I want to multiply this by an expansion of 1 over z plus 2 into the form cn z minus 2 to the n. I need to do an expansion of this function around that center. And the tool is that thing. So now I want you to dig deep in your Calculus 3 background. Because this is a Calculus 3 problem. Take this function and expand it as a power series around that center. I don't start taking derivatives. That's the wrong way to do this. Okay. There's going to be a lot of this kind of manipulation when we're working through Laurent series. Okay, so this is a pretty straightforward one. If I want to expand this as a series that has z minus 2 to the n's in it, then the goal has to be that whatever I'm done, I arrive at something that looks like 1 over 1 minus something that has z minus 2's inside of it. If I could put it in this form, then I could apply that formula to it, right? If I could make this look like that, it's not equal to this, so I'll use an arrow here. If I could somehow algebraically rearrange this thing so it's 1 minus things that have z minus 2 inside of them, then I can feed them into the geometric series formula and I'll get a series out that has z minus 2's. So here's what that manipulation looks like. 1 over z minus 2, I don't even see a minus 2 in here, so I better put one in. So I'm going to write 2 plus z plus, no, z minus 2. There's my z minus 2, but I have to balance it by adding 2 back in so that this is still equal, right? So I've forced there to be a z minus 2 in this problem. So I've induced the z minus 2, because remember the goal is to have 1 minus something that has z minus 2's in it. And I've got 2 problems. First, that's not a 1, and second, there's no negative sign. So the next step is to write this as being equal to 1 over 4 times 1 plus 1/4 of a z minus 2. I'm close now, because that has z minus 2's inside of it, so it almost looks like 1 over 1 minus a brick that has z minus 2's inside. But there's a plus here. Damn. 1 over 4 times 1 minus 1/4 times z minus 2. So that algebraic monstrosity is equal to 1 over z plus 2. If you unwind that, you should get the same thing back again. All I did here was a plus and double negatives are equal to each other. But now this is of the form where it's 1 over 1 minus a brick that I could plug into the geometric series formula?
Are there other ways to expand that?
No,
Okay.
not usefully.
Well, because I think you can do 1/2 times 1 over 1 minus negative z over 2.
So as long as when you're finished, you end up with 1 over 1 minus something that has z minus 2's inside of it,
It has to have z minus 2.
it must have, because we're trying to expand it as a series
right,
with
okay.
2 as the center, right? So sort of algebraically, you are forced into this. You must have a 1 over 1 minus something with z minus 2's in it, or when you plug it into the geometric series formula, there won't be z minus 2's inside of it. Yep.
You could do the same thing, but use z plus to it.
In fact, that's the second half of the question, is to go the other direction. Because you can also expand this series around z is equal to negative 2, which will be the second part of the calculation. So this is equal to, okay, so I'm to make totally clear what's going on here. There's a 1/4 times 1 over 1 minus this brick. And what is inside the brick? It's minus 1/4 z minus 2. And what the geometric series argument says that you do at this point is you take the sum of whatever was inside the brick, and you raise it to the nth power. This is something that you would have seen exhaustively when you work through Calculus 3, when you do, before you know Taylor series, when you're working with power series. This is manipulating things using the geometric series formulas, why they teach you this. So this is 1/4 times the sum of minus 1 to the n over 4 to the n times z minus 2 to the n, which is, can't leave anything hanging outside, minus 1 to the n over 4 to the n plus 1, z minus 2 to the n. So that is the power series expansion for 1 over z plus 2 centered at z is equal to 2. So this is this expansion that we were looking for. I have done way too many steps here, by the way. You can do this much faster than this. This is just the first time I'm doing it, so I'm trying to walk through slowly. And so that means that the series that we're looking for, 1 over z minus 2 times this nasty sum, minus 1 to the n over 4 to the n plus 1 times z minus 2 to the n is equal to, well, I can go one step further here, because I can take this z minus 2 and fold it into these z minus 2's by pushing it inside, and I get the sum of minus 1 to the n, 4 to the n plus 1, z minus 2 to the n minus 1. And if I was being careful, I would have made sure to indicate at every step that my sums run from 0 to infinity. According to the series, what is the order of the pole at z is equal to 2? How many terms with negative powers come out of this series? Just one, right? If you put in 0, you get at z minus 2 to the minus 1. But if you put in 1, you get z minus 2 to the 0. So there's a single term with a negative power. Does that correspond to what we know about the original function? Because that would say that this is a pole of order 1. There's one term with a power of minus 1 in it. Does that correspond to what we know about z minus 2 over here? Well, the power here is also 1. So the fact that this is power 1 and this has a z minus 2 to the minus 1 as its first term is like, that's agreement between the two different ways of looking at the function. Okay. Okay, so that's one of the series that we were asked to compute. So to do the other one, you do the same process, but now you do it with z is equal to positive 2 as the center of the series instead. Okay, so this time I'm going to do this faster. Can I erase any of this? Are people still writing this? Okay, could erase it? Okay. Before I do that, there is one last thing that I want to point out. So let's look at, so what we're claiming here is that if you took f of z, which is 1 over z squared minus 4, and you expanded it on around z is equal to 2, then you end up with the series representation, the sum from n equals 0 to infinity of minus 1 to the n, 4 to the n plus 1, z minus 2 to the n minus 1. What should happen if you integrate that on a closed contour? I mean, we could write this series down. So you start plugging in numbers here. If you put in minus 1 to the 0, you get 1. So it's 1/4. That's the first times 1 over z minus 2. Plus, okay, now you put in 1 and you get minus 1. And then on the bottom here, you get 16. And then z minus 2 to the 0 is just minus 1/16. And if you plug in n equals 2, you get positive 1 over 4 to the 3rd, which is 64, times z minus 2 to the 1st. And then you're going to have a minus 1, 256, times z minus 2 to the 2nd, and so on. From what we know, and from what I asked you guys in the test, what should this thing integrate to? If you just integrated this on a closed contour, naively, not having questions about analyticity, just assume this thing is analytic on this punctured neighborhood, and you integrate around some closed loop, what would the value be?
The closed loop contains.
Okay, it goes right around that singular point. Yep. We've already done a bunch of examples of this, right? So I've got a singular point for the function. I integrate around it. What happens to all these terms when I integrate around a closed loop? All of this stuff is 0, because if you integrated this, all of this is analytic. Turn into f is equal to 0. What is that theorem called? Analytic functions on closed loops integrate to nothing. That's the Cauchy-Goursat theorem or the Cauchy theorem. And what does this spit out if you had your set and the punctured thing where there's the asymptote and you build a contour that goes all around it? What does that thing turn into? 2 pi I, right? It's the only term that survives is this z to the minus 1 term. Right? If you integrated this somehow around a closed loop, what would fall out would be 1/4, which was left over as this coefficient, times the 2 pi I that came from the 1 over z minus squared. So if you did this integral, this is what you would expect to happen. This plus a bunch of zeros, right? So the z to the minus 1 term is super important because it's the only term for which the integral survives, which we've seen several times already and also asked you guys about on the test. This has a name that a bunch of engineers and physicists in the room already know. So this coefficient right here, the coefficient of the z to the minus 1 term, the thing that survives when you take the integral of this series, has a name. It is called the residue of the function. So the residue of f of z is equal to the coefficient, the residue of f of z at a particular singularity. So I have to have chosen which singularity I'm expanding the function around. So the residue of f at a particular singularity is equal to the coefficient of the z minus z naught to the minus 1 term. And it may not surprise you if I tell you that the reason that we compute these series is because it gives us a tool for doing more integrals without having to do parametrization. Parametrization, no fun. As many of you discovered when you tried to parameterize the entire question on the exam about z squared and z to the first and so on. So a very, very special case of a very powerful theorem, which Johnston calls the one singularity theorem. So I'm going to use his terminology here. Says that if f of z has an isolated singularity and z is equal to z naught, and C is a nice contour, closed contour, wrapping once around z is equal to z naught, then the integral of f of z dz, so the setup here is we've got a contour, it's a simple closed contour that goes one time around this singular point at z is equal to z naught. This is going to be equal to 2 pi I times the residue of f at z is equal to z naught. It's exactly what we see right here, right? If we integrated this function on a closed loop, all of these terms disappear, and what falls out is 2 pi I times that coefficient. So the singularity integrates to 2 pi I, the coefficient's still there. And so this is another way, this gets just absolutely abused by physicists, for example, right? They love this. So this is another sort of, like, this is why we're building all this stuff with Laurent series, and why we've picked out the fact that this term is so important, is that it hooks up with a really sophisticated way of computing these contour integrals. Okay? So we should do another example of how this works. I will say that instead of having to write the residue of f at z is equal to z naught, that this has a notation, which looks like the residue of f at z is equal to z naught is res f z naught, and it's equal to a minus 1 in a series expansion about z is equal to z naught. Yep.
Is it always going to be the -1 term even if it's a higher order?
Yes. In fact, so the next thing we'll do is, why don't we look at a function with an essential singularity and see how the same sort of act works. Okay? So with an essential singularity, we can't get away with this geometric series thing because we're not going to have this sort of nice factoring going on in the background. There's actually two more examples of these things that I want to do. I want to do one essential, and I want to do one where you have to take derivatives of power series, because why not? Okay, so let's see if we can figure out, so here's a question that sort of combines all these ideas together. What is the residue of f of z is equal to e to the 1 over z at z is equal to 0? Now that's an essential singularity this time, not a pole. But the game that we play is the same game. If I ask you what the residue is, or the same question would be, what is the residue of e to the 1 over z calculated at 0? That symbol and this sentence are the same thing. That part of the sentence are the same thing. We need to produce a series for this thing that converges on the punctured disk not including 0. Let's say the deleted neighborhood at 0. And then I need to know the coefficient of the e to the minus 1, or sorry, the z to the minus 1 term. So for essential singularities, often what we're going to be doing is these composition type arguments instead. Since e to the z is equal to the sum from n equals 0 to infinity of z to the n over n factorial, as long as z is not equal to 0, I can do e to the 1 over z is equal to the sum from n equals 0 to, I mean, there's nothing wrong with just putting 1 over z in here. It still converges. The function's entire. I can put anything in I want. And if I finish walking this through, this is going to look like the sum from n equals 0 to infinity of z to the minus n over n factorial. If you write that series out, you get 1 plus z to the minus 1 plus z to the minus 2 over 2 factorial plus z to the minus 3 over 3 factorial, and so on. So what's the residue? It's the coefficient of the -1 power term, which is right here. So the residue of e to the 1 over z for the series centered at 0 is 1. That also lets us compute by this one singularity theorem. I could integrate this function with a contour. Yep. Oh, wait, you don't even. Caleb,
I wasn't raising my hand.
what are you doing in here?
Spectating.
Hanging out, enjoying some
absorbing
complex
knowledge.
analysis? All right,
Yeah.
osmosing. Okay, so what is the one singularity theorem say that we should do? Suppose that we took a contour C where one symbol that he likes to use all the time is this boundary of the complex unit disk, right? So let's integrate on the boundary of the disk, which is just the unit circle, the function e to the 1 over z dz. You could parameterize that if you really wanted to, or you could do a really complicated calculation involving using a contour and then letting limits take place. But what the one singularity theorem is going to do once we've built, I mean, in its full glory, it's called the residue theorem. But this lets us immediately say what that is. So what is it? 2 pi I. Ah, it's like that should strike you as absurd that we can do that, right? This function is way, way worse than 1 over z. And yet, if the one singularity theorem is to be believed, this is 2 pi I times the residue at that point. So we get 2 pi I. So it's going to turn out to be the case that being efficient at computing Laurent series is going to be, or sorry, we don't know what Laurent series is yet. Computing these series expansions at these values that are singularities is going to turn out to be really important. So I'm going to walk you through the example I did right before I came to class, or maybe you guys can walk me through the example. What would you do if I increased the power of z by 1? So consider this function. F of z is equal to 1 over z squared times z minus 1. Suppose that I asked you to compute the residue of f at 1. Is there a question? Did I lie? All right. I do lie occasionally. I don't mean to. So if I do, you can point it out. Or not suppose. I want to find. Find this. Yeah, suppose some residue. Find it. What is this asking me to do? What center do I need my series expansion to be at? 1, right? So I need a series expanded at z is equal to 1. Well, I already have a z minus 1 floating around in here. That's good. So I've got 1 over z minus 1 times 1 over z squared. If I did have a series that was built out around z minus 1, I could just multiply this in at the end. But now I'm faced with the arduous task of finding a series for 1 over z squared centered at z is equal to 1. And I'd be impressed if anybody remembers how this trick goes. Yep.
You mentioned derivatives earlier.
Oh, yep, that's the
So
way
I'm
to do
assuming
it.
You
So here's
solve for 1 over z and then take, or minus 1 over z and take the derivative.
yeah. So what you're going to do is the flow for this is 1 over z squared is actually quite difficult to compute a series for. So what we're going to do is we're going to find a series. So step 1, we're going to find a series for 1 over z centered at z is equal to 1. And then step 2 is we're going to take its derivative. Because d by dz of 1 over z is equal to minus 1 over z squared. So if I can get a series for this function, I can get a series for 1 over z squared by taking the derivative. And that absolutely should remind you of the power series section of calculus 3. However many, million years ago that took place. Okay, so step 1. How am I going to rewrite this so I can apply the geometric series argument to it to get a series centered at z is equal to 1?
Minus the quantity z plus 1.
Okay, so I better do 1 over 1 minus
Or no. Minus,
negative z minus 1.
Yeah.
Does that look right? Negative z is positive z. 1, okay, and then this is a negative. Too many negatives, positive. Okay,
Yeah.
negative is positive, so that's negative, so it's 1 minus 1, so I just get z back out again. So this is all equal to z. I'm good. That's a really terrible way of writing 1 over z, but it's necessary if you want to compute one of these series. And what the geometric series thing says now is that you can take that brick and plug it into the geometric series formula, which gets you the sum of -1 to the n over nothing. I don't know why I wrote that. -1 to the n z minus 1 to the n. So this is the expansion of 1 over z around the point -1. Is that okay? This is just the geometric series idea. But that's not the series I was interested in. The series I'm interested in is 1 over z squared. So step 2 says, if I took the derivative of this, it would be equal to the derivative of this. So computing d by dz, I get -1 over z squared is equal to the sum from n equals 1 to infinity of -1 to the n times n times z minus 1 to the n minus 1. If you haven't differentiated power series in a while, this is what it looks like. That's also not quite the series I want because there's this extra -1 floating around. So if I multiply both sides by -1, I get 1 over z squared sum from n equals 1 to infinity of -1 to the n plus 1 n z minus 1 to the n minus 1. So that dude right there is a series expansion for 1 over z squared on the domain of interest. Is that okay? Generally, you'd hope that there was a better way to do this than Laurent series when we eventually arrive here, because you can imagine if there's like a z to the 4th down here, that's a lot of derivatives. Okay? Let us continue. That means that, what were we even trying to do? Oh, we're trying to find the residue of f at 1. So that means that 1 over z minus 1 times 1 over z squared is equal to 1 over z minus 1 times the sum from n equals 1 to infinity of -1 to the n plus 1 times n times z minus 1 to the n minus 1. But now I've got an extra copy of z minus 1 I can throw into the series. So if I divide out by another z minus 1, I get n is 1 to infinity, -1 to the n plus 1, and z minus 1 to the n minus 2. This is the series of interest. Does it have a -1 power term? Because if it doesn't, man, we've done something wrong, because it sure looked like this thing had a 0 or a pole of order 1 at the very beginning, right? So what is the first term of this series the way I've written it? 1 goes, it's 1 times 1 times z minus 1 to the 1 minus 2 plus some stuff. So it's 1 over z minus 1 plus stuff. So the residue of f at 1 is 1. Yep.
So in this case, okay, sorry, never mind. I just actually made a question.
Yeah. So if you wanted to do this the other way is actually much easier here, because if you wanted to do the same expansion but to do it at 0, this is almost, you just take out the -1 and you can directly apply the geometric series. So I'll leave this question for next time. Calculate the residue of this function at the other singularity. And you should expect that if you do it the other way, there's going to be a z to the -2 and a z to the -1 term, because this has a pole of order 2 inside of it. So there should be 2 negative power terms in the series when you're finished with it. Okay? Yep?
It doesn't make sense for there to be a residue if you're not centered on a singularity.
If you're centered at a different point, then you're a Taylor series because you're analytic. And in that case, can there be a -1 term? So the residue has to be 0 in that case. So analytic functions have residue 0. Yep.
When you expand this around the other